Today we're going to talk about repeated measures ANOVA. So the repeated measures ANOVA is a lot like the regular one-way independent samples ANOVA that we've been talking about. But it's also a lot like the paired samples t-test. And so we're going to talk about why we need the repeated measures ANOVA. Then we're going to contrast the independent samples ANOVA with the repeated measures ANOVA. And finally, we're going to break down that repeated measures F statistic into its component variance parts. Okay, so previously, when we talked about one-way ANOVA, we talked initially about why we needed it. And the reason why we need ANOVA is that the t-test is limited. So previously we talked about this example, who uploads more pictures, Latino, white, Asian, or Black Facebook users. When we saw this problem and we thought about maybe doing independent samples t-tests, we realized we would have to do a whole bunch of little t-tests. Well, let's look at this problem. It's similar in some ways, but it's also a little bit different. So here's this question. Which photo type is most frequently used on Facebook? Tagged, uploaded, mobile uploads, or profile pictures? Now, in the same way that this has many groups, this problem also has many groups. So one thing you could all sort of immediately tell off the bat is if we tried to use t-tests, we'd also have to use a bunch of little t-tests here. But here's another thing. These variables are actually linked to one another. Often people who have tagged photos have a number of uploaded photos, who have a number of mobile uploads, who also have a number of profile pictures, right? So in this sense, although these are made up of 4 just separate groups of users, and the user here isn't linked to any of the users in the other groups, Latino, white, Asian, Black groups, right? Here, we have these 4 sets of data, tagged, uploaded, mobile, or profile pictures. But the number of tagged photos is linked to some number of uploaded photos, probably because they come from the same person, and maybe this person owns a digital camera that they really love and carry around everywhere, right? So these scores in these different groups are actually linked to each other. And these are what we've called previously dependent samples, or we've called them paired samples before, because there were only 2 groups of them at that time. But now we have 4 groups, but we could still see that linked principle still holds. So here we're talking about different samples, right? Multiple number of samples, more than 2, but these samples are also linked to each other in some way. And because of that, those are called repeated measures. Because we're repeatedly measuring something over and over again. We're measuring photos here, measuring photos here, measuring photos here, measuring photos here. And because of that, this is called repeated measures. It's very similar to the idea of paired samples, except we're now talking about more than 2. So 3, 4, 5, we call those repeated measures. So we have the same problem here as we did here. If we have a bunch of t-tests, if our solution is a bunch of t-tests, we have 2 problems, whether they're paired t-tests or independent samples. So in this case, they would be paired, right? So even in the case of paired t-tests, we have the same problems that we did before. The first problem is that with so many t-tests, the probability of false alarms goes up. So this is going to be a problem. And it's because we reject more null hypotheses. Every time you reject a null hypothesis, you have a 0.05 chance of error, right? So we're compounding that problem. The second thing that's wrong when we do a whole bunch of little t-tests instead of one giant test is that we're ignoring some of the data when we're calculating the population standard deviation, right? So when we estimate that population standard deviation, the more data, the better. But if we only look at two of the samples at a time, then we're ignoring the other two perfectly good sets of data, and we're not using them in order to help us estimate more accurately the population standard deviation. So we get a poor estimate of S because we are not using all the data at our disposal. Right? So that's a problem, and we need to find a way around it. Thankfully, Ronald Fisher comes to the rescue with his F-test. Okay, so the ANOVA is our general solution to this problem of too many tiny, tiny t-tests. But so far, we've only talked about ANOVAs for independent samples. Now we need an ANOVA for repeated measures. So the ANOVA is always going to start the same way, with the omnibus hypothesis, one hypothesis to rule them all. And the omnibus hypothesis almost always says all the samples come from the same population. So the mu of the first group of photos equals the mu of the second group of photos equals the mu of the third group of photos equals the mu of the fourth group, right? And the alternative hypothesis is not that they're all not equal to each other, but that at least one is different, is an outlier. And so the way we say that is that all mu sub p's, all the mu's of the different phototypes, are not the same. Now, we have to keep in mind the logic that all of these mu's are not the same. That's not the same as saying all of the mu's are different from each other, right? When we say all of them are not the same, if even one of them is not the same, then this alternative hypothesis is true. All right, so this starts off much the same way as independent samples. From there, we go on to analyze variance. Sorry, this should say step 2. So from there, we go on to analyze variance. And here, we're going to use that F statistic again. And Ronald Fisher's big idea that he hit upon is this idea that when we talk about the F, it's a ratio of variances. And really, one way of thinking about it is the ratio of between sample or group variability over the within sample variability. Okay? And another way of thinking about this is it's the variability we are interested in. And I don't just mean that, oh, we're passionate about it or we find it very curious, but I really mean it's the variability that we're making a hypothesis about over the variability that we cannot explain. We don't know where this other variability comes from. It just exists and we have to deal with it. Okay. And so this F statistic is going to be the same concept. This same concept is going to come up again when we talk about the repeated measures version of the F. There are going to be some subtle differences, though. Okay, so let's talk about the independent samples ANOVA versus the repeated measures ANOVA. They both have the same start. They have the same hypothesis. Not only that, but they both have the same idea of taking all the variance in our sample and then breaking it down into component parts. Now, when we talk about all the variance in our sample, we really mean what is our sum of squares total? What is the total amount of variability away from the grand mean in our entire data set? And we could easily, just from this sentence, we could figure out what the formula for this would be. This should be something like the variability of every single one of our data points, right, minus the grand mean, which we signify with two bars, so double bar, squared, right? And how does the sigma know to do this for every single data point, not just the data points in one sample? Well, the way it knows to do that is because this should say n total. So this is going to go through every single data point in every single sample and subtract, get the distance from the grand mean, and then square that distance, and then add those distances all up. Squared distances all up. Okay, so that's the same idea to begin with. Now we're going to take this SS total and break it down into its component parts. Now in independent samples, what we see is that all of the variability that we're unable to explain lies within the group. All of the variability that we are very interested in, that is between the groups, right? And so in independent samples, the story becomes SS total is a conglomeration. It's when you split it up into its parts, you see that it's made up of the sum of squares within the groups, inside of the groups, and the sum of squares between the groups added up. Right? And because of that, the F statistic here becomes the variability, the variance between over the variance within. And obviously each of these variances correspond to its own sum of squares. Now, in a repeated measures ANOVA, we're going to be talking about something slightly different because now we have these linked examples, linked data, right? So here, the data is independent. These samples are independent. They're not linked to each other in any way. But here, these samples are actually linked to each other, either by virtue of being made from the same subject or the same class produced it or something about these scores. They're linked to each other, right? So not only is there variability across the groups, just like before, so sort of between the groups, right? And variability within the group. But now we have a new kind of variability. We have this variability caused by these different linkages. These all are different from each other, but maybe similar across, right? So the person who owns a digital camera, they might just have an enormous number of photos all across the board. The person who doesn't have a digital camera or not even a smartphone might have a low number of photos across the board, right? So there are those things that we call, often are called individual differences. Those are differences that we can actually mathematically quantify, right? We could actually explain where it is, but we're not actually interested in it in this study. We're really interested in this between group difference. But this isn't all. Once you've taken out this individual variability, there's still some residual within group variability left over. And so that's really stuff we cannot explain. It's not caused by the individual differences. It's not because it's between groups. It's just within group differences. So in repeated measures, the sum of squares total actually breaks down slightly differently. Even though it's still this idea of breaking down the sum of squares total, now it actually splits up into sum of squares subject, right? These individual links, that's the yellow part, plus the sum of squares within, just like before, except now we call it residual, because this, we've taken out the variability that comes from the individual differences. And so because of that, there's only a leftover. And so because of that, we call it residual, which is like the word leftover. And of course, the sum of squares between, which is what we're actually very interested in. All right. So just to recap, this is something that we could explain. However, we're not interested in. This is something we cannot explain. And this is something we are very interested in. So our F statistic will actually become our variability between divided by our variability residual. And in fact, we just want to take this guy out of the equation. We want him to, out of the equation of F. So F, it doesn't count the variability from the subjects or individual difference. They're not interested in that. Okay, so if I wanted to show you this in a picture, here's what I would show you.